In section 6.2, we'll be discussing Riemann sums. So let's take a look at this function graph to the right. How would we estimate the integral from 0 to 6? So remember that this means the area from 0 to 6. So we're trying to estimate this part underneath the graph. And so you might start by looking at rectangles, like, oh, I could take a big chunk here. That would give me some area. Then I could add another rectangle here, maybe a triangle over here, and just use geometric areas to approximate. But I'm willing to bet that you actually started with rectangles. And so what we want to do is try to find an ordered, structured way to estimate the area under a curve. And so what we're going to do is use rectangles of equal width. So we might want to decide first how many rectangles we will use. So we'll call those subintervals. And we'll decide how will we determine the height of each rectangle. So our options will be either left endpoint, midpoint, or right endpoint. So a few things to talk about. N is our number of subintervals. And delta x is the width of our x values there, our change in x. We've seen that notation before. And so the way we find that is b minus a over n. The a and the b are your left and right endpoints. That will give us the width of our interval. So if we take a look at the graphs here on the right, if I'm using the left endpoint, I'm using, for my height, for my first interval, I'm going to use f of a. For my second rectangle, it's going to be f of x sub 1, then f of x sub 2, and f of x sub 3. So you'll notice I don't actually use the height of the last rectangle. If I instead decided to use a right endpoint, then I would start with a rectangle that has a height of f of x sub 1, then f of x sub 2, f of x sub 3, and the last one is f of b. For a midpoint Riemann sum, that means I'm going to use a point that is halfway between my left endpoint and my right endpoint. It does not mean that it's an average of the y values. It's actually the middle of the x values and whatever the y value is there. So let's actually work on estimating some integrals with these Riemann sums. So number one, it asks us to approximate that integral 0 to 6 of f of x using a right-hand Riemann sum with 3 equal subintervals. So the first thing you want to do is find how wide your intervals have to be. And so we have 3 equal subintervals. We're going to use that formula, delta x equals b minus a. So that's 6 minus 0 over our number of subintervals, which is 3. So that means that each interval will have a width of 2. In other words, each rectangle will have a base of 2. So when I'm looking at my area from 0 to 6, I'm stopping at 6. I will have to have one rectangle that goes from 0 to 2. Another one that goes from 2 to 4. And then my last one will go from 4 to 6. Now I want to find the area, I want to find the height so that I can find the area of those rectangles. So I know that I want my base to be from 0 to 2. When I'm using a right-hand Riemann sum, I'm going to use the right side of that base, go up until I hit the graph, and then that point will be the height of my rectangle, sorry. So I want to find the area of that rectangle. The next rectangle, again, would go from 2 to 4. I'm going to use the right side to go up on my graph, and then that will be my height. And again, from 4 to 6, I'm going to use the right side as my height. And so I'm trying to find then the area of this rectangle plus this rectangle plus this rectangle. So let's calculate what that would be. Our width is 2 times our height is going to be at f of 2 plus 2 times f of 4 plus 2 times f of 6. And again, I'm just using those right endpoints, 2, 4, and 6 of our intervals. Now, you can factor out that 2. If your intervals are evenly split, then you can factor that out. So that's our delta x. Our f of 2 was 7. That's the height of our first rectangle. The next rectangle had a height of 5. And the last rectangle had a height of 1. So this gives us a total area of 26. Now in part B, it asks us to use a left-hand Riemann sum with 3 equal subintervals. So we're still going to have a delta x of 2. And so I'm going to start the same way. I'm going to go from 0 to 2 as my first interval, but this time I'm going to use the left-hand side as my height. So I'm going to go up until I hit the graph, and then that point will tell me what my height is. So f of 0, which is 8. Then from 2 to 4, I'm going to use my height at 2, go up there. That will be the height of my rectangle. And then the last rectangle from 4 to 6, I'm going to use my height at 4 and draw my rectangle there. So I want to find the area of these 3 rectangles. And so again, we have a width of 2. My first height is f of 0 times, plus 2 times my next height, which is f of 2, and then my last height, f of 4. So again, notice in this case, we do not use the f of 6 when we're calculating this. Because we have the graph here, you wouldn't necessarily have to write out that first step, but it's going to be helpful when we have functions if you write it out that way. So we have 2 times 8 plus 7 plus 5, which gives us 40. Now we'll also want to talk about if these estimates are overestimates or underestimates. And so what we can tell is the sum that we just did, because each rectangle is actually above our graph, then the left is going to be an overestimate. And the right, because each rectangle was below my graph, is an underestimate. And so I want you to think about, do you think it will always be this way? If not, then think about a way that you could draw a graph where my right sum would be an overestimate and my left sum would be an underestimate. Now another question is, how could we make our approximations more accurate? So if I look back over here, I have some graphs that are bigger, some that are smaller. So some things that we could do to make our graph more accurate is we could make smaller rectangles. Or we could do different shapes. Or we could use midpoints. And so you'll see if we draw midpoints, it kind of will overlap and go below at the same time. All right, so in number 2, we have a table that represents the velocity in feet per second of a car traveling on a straight road over a 50-second time interval. We want to estimate the distance the car travels over this interval using various approximation techniques. And so we'll use the table as well as the graphs. So most often on these problems, you are going to have a table, but since we're still setting up this concept, we're going to use the graph as well. So remember that we talked before about if we integrate velocity, it can give us our change in position. And as long as our velocity is always positive, that will give us our total distance as well. So when it says estimate the total distance traveled by the car, it's telling us to estimate the integral of the velocity from 0 to 50. That's what we're estimating here. So the first thing we want to do is it tells us to use 5 equal subintervals. So we're going to use delta x equals, our right endpoint is 50, our left endpoint is 0, divided by 5. So each rectangle will have a width of 10. Let's go ahead and draw this on our graph. We're going to do a left-hand sum. So my first rectangle will go from 0 to 10. But my height is the left endpoint, which is just 0. So it actually doesn't have any area. Next, from 10 to 20, my left endpoint will be at f of 10, which is that 20. And then from 20 to 30, I'll go up to my y value at 20. And this is where the table is going to come in handy because it's hard to see exactly where that point is. But if I look at the table, I see that it's 52. From 30 to 40, I'm going to use the height at 30, which is 80. So that will be my rectangle there. Notice this rectangle is going to go a little bit above and a little bit below. So your rectangles will not necessarily always be above or below. It could be a little bit of both. From 40 to 50, I'll use my height at 40. Okay, so we want to find the areas of these rectangles here. And let's take a look at the graph, or sorry, the table as well. So when I'm going on an interval from 0 to 10, when I'm using the left endpoint, I'm going to think about that left part as my height. And then from 10 to 20, I will use that left value as my height. So that's a way that you can look at the table to help you as well. We do have the graph, so we can use that. So because we have an equal width, I'm going to factor out that 10. Our first height is 0. Our second height is 20. Then we have a height of 52. And then a height of 80. And finally, a height of 77. You always do want to show this step where you have your work and your setup. On the AP test, you can actually leave your answer right there as long as you had units. This is total distance traveled. The 10 was our width. That was measured in seconds. And these values that we multiplied by our heights were in feet per second. So if you think about what the units would be there, seconds times feet per second, that would be in feet. Let's go ahead and simplify this though, because it's going to help us later on. This gives us 2,290 feet for our answer. Now let's do the same thing, but let's do a right-hand sum instead. So for my right-hand sum, same idea. I'm just going to use the right values as my height. I'm going to go a little bit faster now. And so you'll see some of those same values that we had before just kind of shifted to the right. And so when I'm going from 0 to 10 now, I'm going to use the height 20 at first. And then from 10 to 20, I'm going to use 52. So I'm using the right endpoint there. So I'm going to have still 10. Equal width there, times 20 for my first height. I can see that here. And then 52 plus 80 plus 77. And then the last one is 74. So notice here I don't use the left endpoint of my interval, but I do use the right point. And this gives me 3,030. So those are two rectangles that we've already talked about. Let's take a look at another type. So in part C, we want to do a midpoint sum with 5 equal subintervals. And that first rectangle is shown here. So when we do a midpoint sum, our width is still from 0 to 10. But for my height, instead of using the right or the left endpoint, I'm going to go halfway in between them and go up to my height there. All right, and then from 10 to 20, I will use my height at 15 to draw my rectangle. From 20 to 30, I will use my height at 25. From 30 to 40, I will use my height at 35. And from 40 to 50, I'll use my height at 45. So again, it's harder to tell here if this graph is an underestimate or an overestimate, or the midpoint sum is an overestimate or underestimate, and we'll talk more about why that is. But again, what is nice about the midpoint is it is often, if I look at a single rectangle, many times it's both an overestimate and an underestimate if you look at either side. So it kind of evens out a little bit. We should get a better approximation here. So we've got 10 times. Now let's look back up at our table. I'm going to erase these. So for our midpoint, we're going to go from 0 to 10. Oops, I'm still on my eraser. 0 to 10. But my height is going to be 14, the number in the middle there. 10 to 20, my height will be 28, the middle there. So I've got 10 times 14 plus 28. The middle here is at 70. Here is at 86. And the last one also has a height of 70. So this would give us 2,680 feet. Now the last one kind of sum that we'll talk about, it's not technically a Riemann sum, but it's called a trapezoidal sum with 5 equal subintervals. So again, we'll use our same delta x of 10. But this time we're going to draw trapezoids instead. So I'm actually going to erase my midpoint rectangles so that we can be a little bit more clear about what we're drawing here with our trapezoids. So when we have a trapezoid, it's actually going to be on its side compared to what you're usually looking at, or what you're used to seeing. I'm actually going to draw it from 10 to 20 first because I think it will make more sense. So I still have my base from 10 to 20. Then my height, or my base 1, goes up to 20, and my base 2 goes up to that point that was 52. And then I connect those 2 points to get my trapezoid. So I'm looking at this area here. Now from 0 to 10, why I said it was confusing before, since this one's at 0, my y value is 0, this is actually a triangle and not a trapezoid. From 20 to 30, same idea. I'm just going to essentially connect the endpoints there of each interval. From 30 to 40, connect my endpoints. 40 to 50, connect my endpoints. So you can see in some places this fits the graph a lot nicer than just the first rectangles that we used. A reminder that our area of a trapezoid, this is on your stuff you must know cold sheet, is half base 1 plus base 2 times your height. What we're going to do, I'm going to reorder that a little bit. It's going to be half times your delta x. That's handy if your delta x is the same. You can factor it out. Times f of x1 plus f of x2. Those are your heights there. And so just to label that, this is your base 2, this is your base 1, this is your height, because our trapezoid is actually on its side here. So when we're setting up our formula, we can factor out the 1/2, and we can factor out our delta x, which is 10. And then we're going to do the base 1 plus base 2 for each trapezoid. So for the first trapezoid, it's 0 plus 10. Or sorry, 0 plus 20. Plus the next trapezoid is 20 plus 52. So the two heights there, 20 and 52. Plus 52 plus 80 for base 1 and base 2. Plus 80 plus 77. And then the last one is 77 plus 74. And so again, on an AP test, you would want to leave that just like that. You don't have to simplify it. We are going to do it for our sake. We will get 2,660 feet here. One thing you might notice is that those terms in the middle, we actually use twice. And so that's a shortcut that you can use, and that's because if I look at the middle ones, those heights are used for a trapezoid on both the left and the right. I wouldn't do it for my height at the very left or the very right, but those values will repeat in the middle there. The last thing it asks us is to find the average of A and B, and what do we notice? So A was 2,290, so we're going to do 1/2 2,290 plus B was 3,030. If I take half of that, because we're doing the average, I will get 2,660. And so what you'll notice is that that's actually the same as the trapezoidal sum. So the average of the left and right will give you the trapezoidal sum. A lot of people think it will be the midpoint, but again, the midpoint is not the average of the y values on the interval. It goes at the middle of the x values and then whatever the height is there. So if you've already found your left and your right sums and you want to find trapezoid, you can just take the average.